All right, guys, so I asked you to explore these situations. When we have polynomial functions, we want to know if we have an even degree, what happens to the end behavior? What did you notice when you had an even degree with the end behavior? You might notice anything when they were looking? All right. Well, then let's look at Desmos here. I have one in here that I was looking at. So here I have an even degree because I have x to the fourth. That's the degree, 4. That's an even degree. What do you notice is happening here at the end of the functions? It's both going in which direction? Up. They're both going up. So what we're going to put then is, for an even degree, look at it again. And then what about the leading coefficient being positive? See how the leading coefficient is positive? So when that happens then, we would say that it goes like this. It goes up at both ends. All right? So now let's look at when we have an even degree. So see how now I still have an even degree, 6. But now I have my lead coefficient negative. And let's look at that. So now what happens to it? Now they're both going what? Down at the end. You don't need to write this down yet, guys. We'll have it somewhere else too. So now it's going down. So what can I say then about this end behavior? Are they going in the same direction at both ends for this situation, or opposite directions? Same. So when we have an even degree, it's always going to go in the same directions at the end. Okay? When that leading coefficient's positive, it goes up. When that leading coefficient's negative, it goes down. So then, on Desmos, I made a couple of odd degrees. So let's look at this one. What's true of the leading coefficient here? It is, the lead coefficient is going to be positive or negative. Which one? Positive. And look at the end behavior here. So I would say then that when I have that odd degree and we have it with a leading coefficient that's positive, it went like this. Okay? So then I just wanted to check, what about if I have some odd degree, but that lead coefficient's negative? And see what happens now? The end behavior, on this end it's going up, on this end it's going down. Okay, so let's jot that down then. So now it's the case that this is going up and this is going down. So what's true in both of these cases? Is it going in the same directions at the end or opposite? Opposite. So this is always going to be opposite. Okay? So now we're going to take a look at our student journal and the way that our book describes this. So go to page 78 on your student journal. So looking in your student journal at page 78. So when we are looking there, the first situation they give us is odd degrees. What did we say about odd degrees? Does it go in the same or opposite directions? Opposite directions. And notice how here they're giving us an example. When the lead coefficient is positive, it's going to have this type of end behavior. So we call that this situation. Look at the way that they write it though. They say f of x, what does f of x mean? So y is going to negative infinity as x is going to negative infinity. That means the same thing as this. So as x goes down here to negative infinity, y is also going to negative infinity. This part means y is going to positive infinity as x is going to positive infinity. All right? So this is the more technical way of writing that. Okay? Look over here. This one is saying y approaches positive infinity as x approaches negative infinity. So in this situation, as x goes down to negative infinity, y is going up to infinity. So this one would be this situation here. When you're taking a test or something, we'll do it both ways. Sometimes we'll have it written like this for in behavior, and sometimes we'll have it written like this. I'm sure you would prefer the arrows, right, instead of this. But you really do need to understand what that's saying. So what about these even degrees? They're showing us some even degrees. What's happening at the end? It's going in what? Same direction. And so we need to know that when we have a positive leading coefficient, they both go up. Negative, they both go down at the ends. All right? Let's look at some examples now. So let's go over here to these problems. It's going to ask us to decide whether the function is a polynomial function. Well, in order to have a polynomial function, we have to meet these requirements. The exponents must be whole numbers. So in order to have a polynomial function, the exponents must be whole numbers. Whole numbers are these. It's this set, 0, 1, 2, 3, etc. We cannot have negative exponents, or else it's not a polynomial function. So check out number 1. Are all of our exponents whole numbers? Yes. In fact, what's the exponent on the x here? 0. Yeah, x to 0 is just 1. Okay, so now it's asking us, write it in standard form. So in standard form, it would look like this. Leading is going to be the highest exponent, and then we need to go in descending order from there. What's the degree here, everyone? 4, right? And so what type of function is it? When it's to the 4th power, what's it called? Quartic. Quartic. Q-U-A-R-T-I-C. Degree 4 is quartic. And then the leading coefficient. What's the leading coefficient? -3. With arrows, would you know what it would look like?
Yes.
Which way? Up, up, or down, down? Down, down because of the negative. Degrees even. Looks like that. All right, what about this one? The exponent here is 3. What's the exponent really there? -1 is right. That's x to the -1. So would that work then? Is that going to be a polynomial function? No. Okay, let's look at this one. All we have to worry about are those exponents. Is that exponent okay? That is not under the radical. Only the 15 is under the radical. So is that okay? It is actually. Okay, so this is going to be already, it's in standard form. What's the degree? 1. The leading coefficient, just is it positive or negative? Positive. And what type of function would this be? X to the first is linear, yep. All right, looking at this one, is it a polynomial? Yes, put it in standard form. Okay, what's the degree? 2. What's the type? Yep, quadratic. And what's the lead coefficient, positive or negative? Negative. So if it's negative, what's going to happen? Is it going to go up, down, down? It's going to go down, down at both ends. That's because this is an even degree, and negative, that's like this. All right, what about if we have to evaluate a function? Back before you were in this class, you would have just plugged in 2. But how could you do it now? Synthetic division. We're not going to do these, but you should know that they can be done with synthetic division. In exercises 7 and 8, describe the end behavior of the graph of the function. So I want you to use the arrows, and I want you to do those 2 on your own. Kayla, what did you put on number 7?
I put down.
Down, down, do we agree?
Yes.
Yes. Okay, what about number 8? Abby, what did you put on number 8?
Down, up.
Do we agree?
Yeah.
Yep. And the way that this could be written, this part right here, just let me write it out. You don't need to, but just watch. I could say f of x is approaching negative infinity as x approaches negative infinity. This would be saying f of x, the y value, approaches positive infinity as x approaches positive infinity. You will have to be able to write it both ways. You'll want to look back if you need to. Okay, number 9 real quick. Describe the degree and the leading coefficient for this one. What would the degree have to be based on that end behavior? The degree would have to be what, even or odd? Odd. What would the leading coefficient have to be, positive or negative? Negative. That's the kind of thing you need to be able to do. All right, let's go on over to page 80. We're just going to do numbers 12 and 13. Number 12, sketch a graph of the polynomial function if f is increasing when x is less than negative 1, and it's increasing when x is in between 0 and 1. F is decreasing when x is in between negative 1 and 0, and x is greater than 1. Also, f of x must be less than 0 for all real numbers. Okay, so first we're going to do this graphing. So I'm going to make my axes. I like to look at this part first. What is this saying? F of x has to be less than 0. What's f of x mean? So my y values must always be less than 0. Where am I going to have to keep them then? Below the x-axis, right. So now I'm going to go back and read. F is increasing for all the x's less than negative 1. Here's negative 1. I got to stay below the x-axis. I'm increasing until I get to negative 1. What happens in between negative 1 and 0? Well, it says my function has to be decreasing. So I make it look like that. What happens in between 0 and 1? The function has to be increasing. And then what happens when x is greater than 1? My function has to be decreasing. So it's going to be that kind of M shape. That's something you'll need to be able to do. Describe the degree. What would the degree have to be, guys? Even or odd? Even, good. And does the lead coefficient need to be positive or negative? Negative, good. All right, number 13. The number of students in thousands who graduate in 4 years from a university can be modeled by this function, where t is the number of years since 2010. Part A, use a graphing calculator to graph the function for the interval between 0 and 5. Describe the behavior of the graph on this interval. So we go to y equals. We could also use Desmos for this, but I've got my calculator right here. Negative 1/4 x cubed plus x squared plus 23. If I just do a zoom 6, I'm not seeing anything. Well, a little bit there. They say that this works. I'm looking at this over the interval from 0 to 5. So I have to go to my window, and I just want to make it see from 0 to 5, but that's the only time it works. I probably need to go a little higher up to see this. Let's see what happens now. There we go. That's better. So what's happening right here, guys? Is that increase or decrease? So it increases, then decreases. So the behavior is increase, then decrease. Okay, so now it says what is the average rate of change in the number of four-year graduates from 2010 to 2015? Do you guys know what average rate of change means? It just means the slope. It means the same thing as the slope. So they're asking us from the beginning to the end, what's the average rate of change? What's the slope? How do we find slope? Yeah. How could I find these values? I could plug in 0 and 5, couldn't I? Remember how 2010 really represents 0. So I need to know when t is 0, what's f of t, and when t is 5, what's f of t. Where could I go to quickly get that information? Yep. So go to the table. So at 0, we had 23,000. I'm just going to call that 23. And in 2015, we had 16.75. So to find that average rate of change, I'm just going to abbreviate that, I have to do y minus y over x minus x. So when we subtract those, we're going to get our negative 6.25 over what, guys? All right, so now what would you have to do then to simplify? So can you simplify that now? However you'd like to do that?
You didn't bring your phone? How do you survive?
I can't. You know, I'm perfect. I'm always on my phone, aren't I? Yeah, let's say me too.
Okay, so find the average rate of change.
You got your phone.
What did we get? Raise your hand if you can tell me what you get for that average rate of change. Mary? Good job. You're welcome. Okay, so now it's asking us, do we think that this model could be used for years before 2010 and after 2015? What do you guys think? You don't think so? Why? She doesn't know. All right, so what we could do is we could extend our window back, right? So we could extend our window back to -5 and up to like 15.
Actually, I should hear mine in units.
You think yes? It might be okay back here, but would it make sense to have a negative number of people who graduate? No, that wouldn't make sense. So probably not. So I would say no, can't have a negative number of students. All right, so any questions on that?